Okay, so now we're back in section 3.1 and we're looking at correlation. Correlation is also known as your R value. So when I'm asking you for the R value or the correlation, that's what I'm looking for. The R value measures the strength of the linear relationship. So if you're looking at a curved relationship, you really shouldn't be looking at your R. So the strength of our linear relationship. And really we're looking at how close does the data come to forming that straight line. So how close to that straight line is it really becoming? And don't get me wrong, a curved relationship, depending on how close you get to the curve or how weak of a curve it is, it could actually look or have a really high correlation because it's really close to forming a straight line anyway. But we still, if we can see a curve type of pattern, we need to stay away from correlation and using our straight line methods. So facts about correlation, and these are things that you need to know because these are things that are really big on multiple choice questions. So your facts on correlation are things that are going to pop up over and over with multiple choice. Correlation is always between -1 and 1. It can never be higher than 1, and it can never be lower than -1. A correlation of 0 means there is no pattern whatsoever. You can't tell if it's going up, you can't really tell if it's going down. It's really hard to work with, and we had one of those problems on our last set of notes. The closer that a number gets to 1, the closer the dots come to forming a straight line with positive slope, also known as positive association. So if our slope would seem positive, that's our positive association. Now the closer a number gets to -1, the closer these dots come to forming a straight line with negative association. So we get these strong relationships the closer we get to 1, because this is going to be our positive association with positive numbers, but we also have a really strong relationship over here as we get close to -1, because these are going to be our negative associations. And typically when we're looking at this, for it to have a strong association, it's got to be 0.8 correlation or higher. So that is really strong, really close to that straight line. We have a moderate anywhere between the 0.5 and the 0.8 on either side. And anything between 0 and 0.5 is what we would call weak. So a lot of scatter to it. Now, this is just a guideline to help you. It's not, of course, the end-all be-all. Because a lot of times when you're looking at scatter plots, you don't know the R value. And so it's helpful the more you interact with scatter plots with an R value attached, the more you kind of can tell, is it strong, is it moderate, is it weak, just by looking at it and without knowing the R value. So on this slide, we have quite a few different graphs, and you can kind of tell that some of them have more scatter than others. And in fact, what I'm here to show you is, what do you think the actual correlation is? Now this one, our first one, looks like you could probably make a case for like a negative association, but you could probably make a case for a positive association. Looks just like one we had in our last set of notes. This has a correlation of R, or 0. Because you can't really tell the direction, you really don't know what's going on. Now on this one, a little bit more obvious about it. There is definitely more of a negative association to it. Just tends to have more of a downward pattern. You could probably make a case for positive, but gosh, that's really far spread apart for positive. So really definitely looks negative. And it's a pretty far scatter. This is actually a -0.3 association. So this is what we would call a weak association. Okay, our next one definitely going up. You can kind of tell that. Still kind of spread apart, but a little closer than our last one. This is a 0.5. Still in kind of our weak area. Still a lot of scatter to that. Now our next one, definitely negative, way tighter than the last one. So I would think that it's negative because it's going down. And I think the number is going to be bigger than 0.5. So, but in the negative side. So probably about a negative 0.7. So our next one is going up and even closer, even a tighter fit than the last one. This one's a 0.9. So this is a strong. And going back to our negative 0.7, remember the 0.8 was kind of our cutoff? This is a moderate. And our last one, that is really close to straight line. Not a lot of scatter. Those are very, very close to each other. And this is going down, so it's negative. This one actually has a 0.99. Really, really strong negative association. Now, for those of you who want to play around and test your knowledge of it, and I highly recommend, take 10 minutes and mess around with this Guess My Correlation app. And so here is that web address for that. I'll also put it on the website so you can check it out. But this is what it looks like. This is that Rossmann Chance Applet Association. It's Guess the Correlation. And so you can put in, hey, I want 15 data plots, and I want a new sample, and a new sample, and a new sample. And it'll keep throwing them at you. And you can even put in more dots. I always find it easier with more dots. So I try and start with more dots. So that way I get a good idea. So this is definitely a negative association. But there's quite a lot of scatter to that. I'm going to go with 0.6. Oh, it's negative 0.47. I was kind of thinking maybe 5.5. So now I can go ahead and do a new sample. Ooh, that's pretty tight. So it's a positive one, and it looks pretty tight. Maybe 0.68. Oh, 9.3 was even, see? Look, I'm not even doing a very good job. So let's do a new sample. Oh, looks like we got a influential point, an outlier down here. I can't really tell which direction. I'm going to go with 0. 0.41? What? And remember, this is all calculated mathematically, so it's pretty good. And we can even go in, let's see if we can do a 200 sample. Whew, look at all that. Oh, not bad, 0.85. See, the more dots you have, the easier it is. Okay, so that's enough playing with that. I could probably play with that all day long. So that gives you a chance to just kind of play around, see what's going on. So we're going to go ahead and look at a sample problem. A recent study discovered that the correlation between age at which an infant first speaks and the child's score on an IQ test upon entering elementary school is negative 0.68. A scatter plot of the data shows a linear form. Which of the following statements about this finding is correct? So before we even go into here, if this is my correlation, we know that this is a moderately strong negative correlation. And so since, let's see, what's our explanatory variable? So our explanatory variable is age of speaking. We're using that to predict an IQ test. So if it's a negative association, that means as speaking age increases, so as my explanatory variable increases, my IQ when they first enter school will decrease. And so that's where that interpretation comes in to help with these types of problems. So infants who speak at very early ages will have higher IQ scores by the beginning of elementary school than those who speak later. 68% of the variation in IQ test scores is explained by the least squares regression of age. We haven't even talked about least squares regression or any of that, so we know that's not going to be it. Encouraging infants to speak before they are ready can have a detrimental effect later in life, as evidenced by their lower IQ scores. No, because as the age goes up, so as they get older, the IQ is going down. So this definitely isn't true. There's a moderately strong negative linear association between age first spoken and later IQ test scores for individuals in this study. This is correct. Why is the first one not correct? Because this is looking at cause and effect. And in chapter 4, we learned that unless this is an experiment, we can't say that there's cause and effect. We're saying that kids who do this will have that because this causes that. And that's something we can't do. So the correct answer would be D. Okay, how do we calculate correlation? Correlation is calculated by this formula. And I believe that's in your actual formula sheet. And this is summation, so I'm going to add up all the zx, which is the z-score of my x values, times the z-score of my y values. So for 1 point, I have an x value and a y value. I'm going to find the z-score of that x number, I'm going to find the z-score of that y number, and I'm going to times them. And then I divide by n minus 1. And n is our sample size. So how many data points we have, that's our n. So I have a sample problem here all kind of worked out for you, and I just want to walk you through it so you're not writing a lot. So we have body weight and backpack weight of this camping trip. So on a camping trip, we had these people. One weighed 120 pounds, and their backpack weight was 26. One weighed 187 pounds, and their backpack weight was 30. And so we were looking for a relationship between these. So when we look at our scatter plot, it looks like there's a positive, somewhat linear association, and it's pretty strong, except for maybe this point right here kind of makes it less strong. So how do we do this? So the first thing we do is we take our explanatory variable, which we think is our body weight, and we're going to write that in L1 in our calculator. And then we're going to take our backpack weight, and we're going to put that in L2 in the calculator. And what that allows us to do, it allows us to calculate the mean and standard deviation for each. So that's what we're going to do. We're going to do the mean and standard deviation for the body weight through the one variable stats. And we get a mean of 136 for weight and a standard deviation of 30. For backpack weight, so we have a mean of 28.625 and a standard deviation of 3.46. A lot less variation. That standard deviation is much smaller. Then we calculate the z-score for each. So what I would do here is I'd take 120, I minus the 136.125. So I take the value, I subtract the mean, I divide by the standard deviation. And this is my zx. And then I'd find my zy. So the z-score for my y value, the y value here is 26, minus my mean, divided by that standard deviation. And so on my next slide, that's exactly what we have. We have all of that worked out. So this is person 1, the z-score for their body weight, the z-score for their backpack weight, and those two numbers multiplied together. And then person 2, and person 3, and person 4. And so you can actually do this on your calculator. So what you can do is you can go into your L3 and you could type parentheses L1 minus the mean divided by the standard deviation, and it'll calculate all those z-scores for you. You can program that in there. And then you can go to your L4, your list 4, and say, okay, I want my L2 values. Subtract the mean, divide by the standard deviation, and it'll calculate all those z-scores for you. And then you can go to L5 and times those two lists. And again, it does it for you. And so now we can go to our correlation And our correlation says that now that I've times those z-scores, I can add all these up. So I'm going to add them. And when I add them up, we get 5.565. Then we divide by n minus 1. So we had 1, 2, 3, 4, 5, 6, 7, 8 people. So 8 minus 1 gives me 7. So we do the number divided by 7, and that tells me my correlation, which is about 0.8, which is on the borderline of a strong association. And a strong positive association because it's positive R value. Okay. So, things you need to know about correlation. Again, both values must be quantitative to use correlation, cannot be categorical. If you switch your response variable and your explanatory variable, big one, shows up all the time on multiple choice questions. If you switch a response variable and explanatory variable, your correlation will not change. If you flip the graph around, how close those dots come to forming a straight line aren't going to change. If you change your units, the correlation's not going to change. Correlation has no unit of measure. A correlation close to 1 does not guarantee that it is not curved. So always check for curvature. Look at the graph, see if there's any curvature. Because if there's curvature, you shouldn't be doing any of the stuff we're going to do this chapter. Please remember, it is sensitive to outliers, so look for those outliers. And correlation not only measures how close the data fits to a line, not how it fits to a curve. So be careful about that. That's why we're looking for those curves data all the time. And that's it for section 3.1. So next we're moving on to section 3.2, and we're breaking that up over 4 days because there's a lot of information there.